Okay, I'm trying to record this for a second time. The recording I did yesterday, the audio is kind of screwed up, so let's just jump into this presentation. So this is a quick introduction into Verilog. This is hopefully going to help you accomplish some of the things you need to know for Lab 1. Verilog has a huge learning curve. We've all been there, so hopefully this will make the process a little less painful. Okay, so some of the lesson objectives I want to cover. Hopefully by the end of this, you'll have a better understanding of how to compile a file using iVerilog and how to view a waveform in GTK wave. I'm also going to be going over some basic Verilog syntax. So how do we create modules? And we're going to talk a little bit about delay. I also have a little piece prepared on blocking and non-blocking assignments, which is a nuance that will affect us after Lab 1, but might be cool to look into. But that's not something I really want to be a key takeaway here. And then talking about how we design a Verilog test bench and the considerations we make to create an effective test bench. All right, so for this lesson plan, we're going to build and construct an AND gate in Verilog. We're going to do that by creating a NAND gate and an inverter. That might sound a little counterproductive because the NAND gate is the inversion of the AND gate. So why are we inverting it? And I'm going to show you something in a little bit that'll hopefully make this make more sense. But just bear with that for now. We're also going to build a comprehensive test bench for the AND gate. And we're going to validate the Verilog modules we create. And we're going to check out some of the waveforms in GTK wave. All right, so quick note here. This is kind of how I approach a problem which requires me to write Verilog code. So I usually have an idea, and then that idea I then manifest in the form of a schematic, and only then do I start implementing it in actual code. So if you may have experienced this already, you're like, all right, I need to build this, I don't know, half adder, and you jump into Verilog and you start writing some code and you're like, uh-oh, I forgot what connects to what. I don't know what wire should be where. I don't know what my inputs and outputs are. It can be a huge mess because Verilog is text-based. It's not very visual, so it's hard to see what's connecting where, and it's super easy to get lost. And if you don't plan out your approach properly, you might end up wasting a lot of time. So that's my little preachy bit on that. I'm also going to touch on why an AND gate is being built out of a NAND gate. The implementation in Verilog might seem a little bit silly. We'll get to that in a bit, but here's like the fundamental reasoning why. So if you attended Christia's recitation, you may have seen like the construction of some gates using CMOS devices. On the left here, we are looking at a 2-input NAND gate in its simplest form. It is created using 1, 2, 3, 4 transistors. And if you look on the right, we have an AND gate, which is constructed out of this NAND gate plus an inverter, which is 4 plus 2 transistors. So an AND gate is technically more complex than an AND gate if we're using this kind of this way of creating them. If you don't understand why these transistors create an AND gate or an AND gate, do not worry about it. That is not the intent of this presentation. Okay, let's talk about module creation. So here is a large block of code, and I'm going to break that down. But this is what our end piece will look like. So erasing some of the stuff, we have this. Use a pointer. So this first piece here, we open the module by writing out the word module. We close the module by writing the words end module. So this is kind of like our wrapper, which everything fits inside of. So we say, all right, let's make a module. You type out module, and then you give your module a name. In this case, I call it my module. Slap on some parentheses. We'll talk about what goes in them in a second. And finish that line, or finish this this phrase, I guess, with a semicolon. Verilog is one of those programming languages which require a semicolon. And honestly, it's a bit of a blessing and a curse. A curse because if you forget a semicolon, you might spend 30 minutes trying to figure out why your code is not compiling, only to figure out you forgot a semicolon on line 56. But it's a blessing because we could do stuff like this. We can very easily separate like lines into more digestible chunks. So separating our inputs and outputs, adding white space wherever you want. It helps make the code more readable for creators like me and the teaching team. It'll also help your peers who you are trying to share code with. Okay. So what I just threw in these parentheses are inputs and outputs. The way we do that is we say input and we list all of the inputs separated by commas. And then we write the word output and write all of the outputs separated with commas. In this case, there's only one output and there are two inputs. But make sure everything is separated with commas or else Verilog won't be very happy. What's nice is that if you have many inputs or many outputs, you only have to write the word input once and then write all of the inputs. And then the word output once and then write all of the outputs. It's just a small convenience factor I appreciate. And then you write your actual code between this line and your end module. And we will write some of that code in a bit. Okay, so we've made a module. This is what our finished module looks like. Let's actually instantiate it. So if you're familiar with writing Python code, if you write a function, it doesn't actually do anything until you call the function. That's exactly what we're doing here when we instantiate a module. Instantiation is basically like calling / defining a function in a programming language, but instantiation is like the hardware word. It's a little nuance there. Okay, so there are three pieces to this. The first is the module call, where you write out the name of the module. Next is the delay parameter, which is an octothorpe followed by a number. Octothorpe is the hashtag dude. And lastly, the module instance. So we'll talk about the delay parameter in a second, but this is the general format you want to follow. So first you say, okay, let's call my module, put your delay parameter, and then you make an instance. So this instance can be called anything. You call it my module 1, you call it ANDGate1, device under test 0, whatever, to be clear and succinct about like what you're actually instantiating in your code. And then inside your instance, you want to include your inputs and outputs. And of course, semicolon. Can't forget that. Okay, sweet. Delay parameters. So it's this little bit of text that goes inside your instantiation. What does it mean? In real life, a signal, an electrical impulse, takes time to propagate through gates or buffers or whatever. To more realistically model how a circuit would function, we add delays to our code / models to more realistically simulate / model stuff. So looking at this line down here, the octothorpe followed by a single number will set these parameters to for your delay. So if you just have one number, your time for a rising edge is 5 time units, your time for a falling edge is 5 time units, and the time to turn off is 5 time units. I'm saying time units because we haven't defined what time scale we're at. That's something we write in Verilog. It's one line of code, pretty straightforward, but it would be inaccurate to say this is seconds or nanoseconds or picoseconds or whatever. All right, great. Honestly, for CompArc, this is as much as you need to do for your delay parameters. But if you want to get more fancy with it, there are some cool tricks you could do. It's not really a trick, but you could have parentheses and put multiple numbers inside of it. If you do that, the first number will be your rise time. The second number will be the fall time. And the time to turn off defaults to the lowest value inside your parentheses. So in this case, 5 is a smaller value. So the time to turn off automatically set itself to 5 time units. Well, if you want to get even more granular, you can have 3 numbers inside your parentheses, and those will map directly. So the first one is time for rising edge, time for falling edge, and the last one is time for the device to turn off. You might be asking, all right, cool, what does T rise, T fall, and T off actually mean? And let's talk about it. So state transitions. T rise is the time it takes for a gate to transition from a logical 0 to a logical 1. So if you're looking at the actual waveform, it would look something like this. And then this time here, where we are transitioning from 0 to 1, is the rise time. T fall is the time to transition from a logical 1 to a logical 0, or the falling edge. So the waveform would look like the opposite. And the time is this. Yeah. Last, there's a time for the device to turn off, which is also the time it takes to transition to Z, or the high impedance state, or the tri-state. If you're familiar with designing electronic circuits, you might know, or you might have heard the term like a floating value, or floating node, floating voltage. Floating basically means we don't know what it is. And that's exactly what Z is. Let's take a look at a couple of small circuits to better understand that. All right, let's focus in on the one on the left right now. Supposing this is our Vout node, we know that the output would be 0 if it's tied to ground, which it is here, because this switch is closed and this switch is open. So there's no electrical connection here. If we wanted a logical high, or a 1 on Vout, we would close the switch to VCC, and the switch to ground would be open. So in both of these cases, we know exactly what Vout is. But what would happen if we open both switches and there is high impedance between both VCC and ground? Well, the reality is we have no idea. There could be some straight capacitance on this node that could charge or discharge, or there might be some other circuitry connected to the other end. There might be other EMI like interferences that are affecting the voltage here. So really we have no idea we don't know what is on Vout, which is okay sometimes, but that's what Z is. That's as far as into it I'm going to go. That means that this node is not being driven by a high or a low value. Cool. All right, so back to delay parameters. This is all you need, really, for CompArc. But if you want to get more granular, feel free to do so. Okay, so back to the lesson objectives. Let's look at what we said we were going to do, and let's look at what we actually did. So we have talked about module declaration. We've talked about gate delay. We have not talked about any of this other stuff. So let's talk about it. All right, I'm going to hop out of this presentation and then hop into KiCad, because let's just sketch out our schematic for this project. Okay, in the interest of saving ourselves a little bit of time, I did a little bit of legwork here to get these 2 gates we wanted. Because this example is relatively simple, all we need is an AND gate and an inverter to create our AND gate. Now, make sure we connect everything together. That's our output. And then these are our inputs. Make sure we label them. So I'll add an input A here, add an input B here. Let's have an output that we call Q here. yeah, so this is our exciting stuff. All right, sweet. Now that we have kind of planned out what is connecting where, we can hop into Verilog. So actually, we don't need this. I'm doing this on my Mac because the recording on my Ubuntu is not behaving the way we want. So I'm just going to go to my folder where I want to write the code and then make a new file. So this process should be pretty similar for y'all in your Docker image. The commands are pretty much the same. So you want to make a folder, you can make a folder with makedir, mkdir space, and then the name of your folder, just call this test. And then you could go into your folder with the change directory command or cd, and there you are. But let's talk about actually making the files we want. On your Docker image, I think you have a couple of pre-installed text editors, Vim and Emacs. I'm going to be using Vim here. I'm an amateur at using Vim, but it gets the job done for me. Feel free to use whatever you want. So let's make a Verilog file. We'll call it and.v. .v is the extension for Verilog, and then let's hop into the file. Okay, I guess I can't do that. How do I make this guy a little bigger? That's a little unfortunate. Well, stick that there, stick this here, extend this a bit. Okay. Sweet. So now we are in our file. Let's create a module. So we can't really jump into building the AND gate yet because we need to build our NAND gate and we need to build our inverter. So let's start by building the NAND gate. So I'm going to make the module with our module wrapper. So module, and then let's call it NAND 2. 2 because it's a 2-input NAND gate. Stick some parentheses, and then end module. Okay, next, close the parentheses and add a semicolon, and now we can list our inputs and outputs. So input, we have 2 inputs. We'll call those A and B. It's the same as these, comma, output. All right, so that's listing all of our inputs and outputs. Now we're ready to actually write our implementation in here. I'm going to use built-in functions for and not to actually kind of connect everything together. Yeah. So this might seem a little bit silly in practice, but this is more to get you guys comfortable with like writing modules, stringing them together, and then making test fetches for them. So I'm going to use the and then have the output be Q intermediate, and the inputs be A and B. So, and semicolon. Let's take a second to digest this line. So I'm using this and function, and it is taking the logical and of the 2 inputs A and B and writing that output to this intermediate node that I'm calling Q intermediate. And you may be saying, hey, wait a minute, where's Q intermediate? We haven't defined it anywhere. Like, where's it coming from? And that is exactly right. So what we do when we are connecting things together is we add wires like we do in regular electronic circuits. So let's make an object called a wire and call it Q intermediate, semicolon. So now we have a place for this signal to go, this logical AND signal. Okay, great. But what we just built is a little AND gate, but what we really want is a NAND gate. You might see why this seems silly now, because we are putting an AND, and then a NOT, and then a NOT, and then we have AND. But you know, this is for the sake of practice. So let's use the NOT command, and let's say the output of this NOT is our output Q. The input to our NOT gate is Q intermediate, so we want to flip the signal. Close parentheses, semicolon, boom. We just finished our NAND 2 module. It's pretty exciting. Now, let me get out of here, and let's start writing a test bench. Feel free to pause the video and like copy down the example. I know I went a little bit fast, but let's make another file. So I'll call this one and.t.v. I'm not sure what the naming convention is for this course. I think John calls files test underscore and.v in that format. But personally, I've always done and.t.v. T.t stands for test bench, but like this .t doesn't actually mean anything. The extension is still .v for Verilog. Yeah, that is my piece on that. So let's hop into this file and start writing some code. So what we need to do first is include our and.v file that we just made. So to do that, we use the backtick, the little character next to the 1 on your keyboard, and say include, and then in quotation marks, and.v. Next, we can set a timescale using a command called timescale. So backtick timescale, and the format for this command is timescale, and then you put your units / resolution. So in this case, or in most cases, at least for the sake of Compark Labs, I used 1 nanosecond timescale with a resolution of 1 second. Cool. Okay. So now let's make a module for our test bench. So module, nothing new there. We'll call it NAND2 underscore test. Yep, and let's just do that. What we need now are the inputs and the output for this test bench. And to do that, we're going to use this thing called a register. So to do that, we use like this call or command reg, and then we list out all our registers like we would anything else in Verilog. You might be saying, wait, what's a register? We haven't talked about that yet. And no, we haven't, but in Compark, you'll talk all about registers later in the course. For the sake of explanation right now, we're using a register as a container to remember our inputs, because those inputs are going to be changing during our test. So real quick, just to make sure it's super clear, the point of this test bench is to test the NAND gate we just built. And to test that, we want to see if it works. We want to give it different input conditions and see if the outputs are what we expect. Because we're just doing a simple 2-input gate, there are not that many inputs and output combinations. There's only 4. So we can exhaustively test this. We can list every possible combination of inputs and see if the outputs match. And that's great for us. In the future, you'll probably be working with more complicated circuits, which require more inputs, many more outputs. And suddenly exhaustively testing them becomes extremely tedious and honestly a huge waste of time. That's when you need to start thinking about your edge cases. Like when you're writing these test benches, instead of saying, okay, let's list every possible input, we need to figure out a way to exhaustively test, exhaustively break your code. And that's when the interesting, fun part of writing test benches starts. Another quick anecdote, which I just personally like, I heard that you probably spend 30% of your time actually designing your hardware, and then 70% of your time validating, writing test benches, figuring out if your hardware actually works. The validation step is much larger than the actual design step. Okay, that preachy bit aside, let's also add a wire so that we have like something for our output. So we'll call the wire Q. Okay, great. Now we have our inputs and outputs ready. Next is time to instantiate our NAND gate. So our NAND gate module was called NAND2, and we'll just call this device under test 0. That's what DUT stands for. You might see that. And then we need to list our inputs and our outputs. You saw in the end.v file, I just listed everything like this. And because I knew the order in which input should go on a built-in function, I was able to do that. But to make our lives a lot easier, we can use this cool way of like defining our inputs and outputs to save ourselves some headache. So what I mean by that is inside our module, we have a list of inputs and outputs, and the order is super important there. If you think about like a function in Python, you have inputs X, Y, Z. Input X has to be the first one, input Y has to be the second one, input Z has to be the third one. It's exactly the same with Verilog. If you screw up the order, then your circuit or your simulation will get screwed up. So to save ourselves the headache of having to remember exactly the order we need, we could do this thing called like dot parentheses notation. I actually have no idea what it's called, but if you put a dot and then your variable or your like input / output and some parentheses, you can feed it these registers or wires and it'll put it in exactly the right order. You don't have to worry about order at all, which I think is super helpful. So dot A, and dot B, B. I'm just going to backpedal here a little bit to be extremely clear. Let's say we call this A1, B1, Q1. So if we think about our and.v file, we have the inputs and outputs A, B, and Q. So that's what the letter next to the dot is. These are the inputs and outputs for our NAND module in the other file. Q1, A1, and B1 are the registers and wires in this file, and that's what we're feeding into those inputs and outputs. But yeah, that's just like a trick that I think, not even a trick, it's just something that you should do that'll make your life a lot easier. Get into that? Okay. All right, so we have made our inputs and outputs, our registers and wires. We have instantiated our NAND gate. Let's actually write some tests now. To do that, we use this function, initial begin. And then because we began something, we also need to end it. You might be saying, all right, what's initial begin? What's initial end? Or what is end? Initial begin basically means that when you compile your code and you run it, it'll start executing these lines at time equals 0. So as soon as we compile it, time equals 0, it'll start doing whatever is written in there. So let's say at time equals 0, we want our inputs A to equal 0, and input B to equal 0. And afterwards, we want to test when A equals 0 and b equals 1, when a equals 1 and b equals 0, and when a equals 1 and b equals 1. So this is like our exhaustive list for testing our NAND gate. Every possible combination of A's and B's. Now, this code isn't quite right yet because there is nothing happening in between these operations. So what that means is when you start running this code at time equals 0, A equals 0, B equals 0, then it'll immediately update to 0 and 1, then immediately to 1, 0, then immediately to 1, 1. Which means we'll never see what happens for these first three lines. So to actually see what's happening under the hood, to see what's happening in each of these discrete steps, we need to add some delay between them. So let's add some delay. We add delay with the delay parameter. So octothorpe, I'll just do 5. Okay. And I'm just going to add one more to the end here so that we can see what's happening in this last state for a little bit of time. Okay. Cool. So we have all of our test cases. So we are running these inputs into our NAND gate, and the output will be something. Cool. But there's another problem now. We are doing this, but we have no idea how to see what's actually happening. So currently, we should have something displaying the output. To do that, there are two ways. There is a display function and a monitor function. I'll talk about both. In and let's add this line with monitor. So to use the monitor function, you write $ monitor, open some parentheses, and then it's kind of like an F string in Python. I keep making a lot of Python references. I think most people in this course have taken Python or Softas already. So I'm hoping this makes kind of sense. So I'm going to write some stuff and then I'll talk about it in a second. So $P A equals %B close quotes M A B. I don't know, there's two parentheses here. Okay. So what I did here is on the left-hand side, inside the quotes, there is a string of text. This %t will map to this input time. Time is a built-in function, so it'll tell us how far in the simulation we are. Then we have a equals %b. So this is kind of like your format string. %b will latch onto the input a over here, and then %b on this one will latch to input b over here, and then %b will latch onto input q over here. So the order matters. If you screw up the order of a, b, and q, you might be like, all right, my code is not working, but it might actually be working. So be vigilant of that. B stands for binary, so it's going to output a binary number. We could use decimal, we could use hex. It doesn't matter in this case because we're only dealing with ones and zeros. So because binary is base 2, ones and zeros do exist. But sometimes it might be more useful to look at a hex value or a decimal value than a binary value. Next, I'm going to write a little bit of boilerplate stuff. I can't give you a great example of or explanation of what this means, but we need to make a dump file, which is where like our simulation data goes so that we can view it in waveform. To do that, we use the $dump file function with parentheses, and then we'll just make a dump file called dump.vcd. Make sure you get the .vcd extension. That's important. I don't know what it stands for. And then you have this other function we need to use called dump bars. And then parentheses, semicolon, boom. So now we are running through these cases and we're outputting them using the monitor function. You might be saying, all right, you already have an initial begin here. Why are you doing another one here? And cool thing about hardware is that unlike traditional software programming languages, hardware can operate in parallel. So in your Python script, you're usually going line by line, executing. Maybe you go back up if you have a loop, but you go in like vertical order. That's not true for hardware. If you connect a signal to multiple inputs, it'll all fire in parallel. And that's exactly what's happening here. So at initial begin, at time equals 0, this first block of code will execute, and the second block of code will execute. So both of these are happening concurrently, which is pretty cool. Okay, great. So now we have our test bench made. Let's try running it to see if our NAND gate works. Okay, so to compile Verilog code similar to C, you have your compiler, so I Verilog, then you use -O for output. You give your output file a name. We'll just call this NAND test. And you feed in the file you want compiled. So in this case, it is and.t.v. We want to feed in the test bench, not the Verilog file, not like the modules file. All right, so it looks like we got a syntax error. Let's go back to our test bench. Look at line 24. See if we got something. Yes, so mistake on my end. We never closed our module. So at the beginning of this file, we created a module called NAND2test, and we wrote a ton of stuff inside the module, but we never actually ended the module. So throw in an end module here, and then now it should work. So if it does work, you should ideally see nothing, and you have like a new terminal line to mess with. Now we can see what the output of this file was by using this command, // and then your output file. So in this case, it's NAND test. Sweet. All right. So let's talk about this for a second. What does // mean? / is current directory, and inside this current directory, what file do we want to run? And we're just opening NAND test. If we look over here, at time equals 0, we have inputs A equals 0, B equals 0. At time equals 5, 10 time units, 15 time units, we have all of these inputs in the order that we prescribed. And then we have our outputs exactly what we want. So we built a NAND gate, which means that it'll output false only when both inputs are true, which is exactly what we see here. And the rest of the time, it'll output high or true. So that's great. We just built a NAND gate, but our job is not done. We need to build an AND gate, right? That's what we set out to do. So to do that, we need to build this inverter and then string it all together. So let's hop back into and.v and write our inverter. So make a new module, call it module inverter1. Semicolon and module. And let's have input y, output y inverted. Don't forget to separate everything with commas. And now we can use the built-in not function to make our life easy. So not, and then you want the output y inverted, followed by the input y. Okay, sweet, that is our inverter. I'm not gonna go through the test bench process for that. If you want to do it as an exercise, please do. But let's just jump into actually finishing out this AND gate. So gonna hop back in and make a new module and two input AND gate. Follow the same process as before, parentheses, semicolon, and module. Our inputs for the AND gate are, let's call it A, B, and our output is Q. And you can call these whatever you want, really. A, B, C, D, pretty standard for inputs. Q is a pretty standard value for an output. Try to avoid stuff like Z or X because those mean different things in Verilog. It might make your life confusing or like a third party's life more confusing. Alrighty, so our goal here is to string together the two modules we wrote before. To do that, we need to instantiate both of them inside this module. So let's do our module call. So NAND2. And then we need the delay parameter. Let's just use 5 time units. And then our instance, let's call it NAND gate. Then we should use the dot parentheses notation so that we don't mess up the inputs and outputs. So our inputs and outputs for NAND2 have the names A, B, and Q, right? So let's dot Q, dot A, and dot B. Close parentheses, semicolon. Now, what do we feed into these things? Our inputs, we know, are A and B. But we don't want the output of the NAND gate to be the output of the AND gate also. This is like an intermediate step. So we need a wire in between. So let's make a wire. Wire, we'll call it Q intermediate. Semicolon. All right. Intermediate inside of our parentheses, and boom, we've instantiated our NAND gate. Now let's instantiate our inverter. So inverter 1, delay of 5 time units, and we'll call this inverter. Let's just give these numbers. So NAND gate 0, inverter 0. And then our input and output is Y inverted and Y. So you see that the stuff following the period is the names of the actual inputs and outputs in that module. Okay. So Y inverted is the output, and that's the same as the output of this entire device. So that's what we'll feed Q into. And the input to the inverter is this intermediate node, which is Q intermediate. Semicolon. And that looks like a finished AND gate to me. So we have our end module. We won't run into that problem again. Escape. And then let's hop into the test bench. And we could spend all the time writing a test bench for this AND gate, but let's save a little bit of time and cheat. I'm just going to change all the NANDs to ANDs because we made the naming easy on ourselves. And save that. Run our compiler. All right, so I clowned a bit and made a couple of silly mistakes in the actual file. So what I had forgotten was a semicolon on this line. Semicolons can always get you. And I missed a parentheses here. So That's why we got a compile error. But yeah, now if we run compiler, it should compile fine. And now let's actually hop into the test bench real quick. I'm going to change, actually, let's make the output of this and test, and then feed in and.t.v. Now let's just look at the output, and then it's called and test. And it looks like we built an AND gate successfully. Woohoo! So inputs or whatever, outputs are all 0 until both of the inputs are true, and then the output is also true. Nice. All right. So this is the part where we look at GTK wave. This is going to be slightly different for the Ubuntu users or the Docker image folks who are actually using GTK wave on Mac. GTK wave is a pain, so I installed another app called Scan something, I don't know. But the process is pretty simple. You just go open. I think on GTK wave it's called open in new tab. Navigate to your folder where you have your code. Open the VCD file, and you should have a view that looks kind of like this. So if you click on a module, we have our and2 test module where we have some registers and wires for inputs and outputs. And inside of that, we should have our broken down modules. So we have our AND gate, which is comprised of an inverter and a NAND gate. So if you're curious about what's happening on the NAND gate, you could click on the NAND gate. If you're curious what's happening inside the inverter, you could click on the inverter. Well, let's just take a look at the AND gate right now. To look at the waveforms, you click on a thing and you drag it onto the list. And you can see time steps is in nanoseconds because that's what we set it to. And Q is our output, and it's only high when both A and B are also high. So that's great. If you want to prove that the inverter works, we could see that the input to the inverter should be the opposite of Q, and the output of the inverter should be the exact same as Q. So you can see that. For this example, it's a little silly to like deeply look at the waveforms because it's very predictable. But you might be dealing with some crazy circuit which has weird timing with the clock or requires like super precise, I don't know, timing, where looking at the waveforms in relationship to time could be super, super helpful. That's what this tool is for. Make great use of it. I think it's super, super useful. That's all I got for that stuff. Let's hop back into the presentation real quick. And take a look at some of the other stuff real quick. So this is the timescale command. So time unit followed by a backslash followed by the resolution, and it changes what the octathorpe number means. It says 50 seconds, 50 nanoseconds. It's whatever you set it to. Monitor versus display. I touched on this briefly, but I want to be super clear about it. Monitor prints to the terminal every time something changes. So if our inputs change, monitor will update. If the output changes, monitor will update, which is pretty nice and convenient if we have 4 inputs or 2 inputs and 1 output. But someday you might have a simulation that has dozens of inputs, and printing every single state change would be ridiculous. Like you just have nonsense in your terminal that you couldn't be able to parse through. That's where display comes in. It prints once to the terminal, and it must be called every time you want to print after that. So if you have 4,000 state changes and you only want to look at 15 of them, that's when you use display. The dot parentheses notation allows us to enter inputs and outputs for devices under test carefree. And this is just a quick aside on the register. So register, or reg is short for register. We are just using the register here as a memory device to define our inputs, and that allowed us to change the inputs and like maintain those states during the test bench. But yeah, that's what I got. Hopefully this helped, and you have a better understanding or a better idea on how to approach Lab 1 in Verilog.